Because I'm having issues downloading the handwritten version of this derivation, I thought I would do a PowerPoint presentation. So this is the derivation of the Michaelis-Menten equation. To start, we're going to look at what is the Michaelis-Menten equation. And simply put, the Michaelis-Menten equation describes the kinetics of enzymes as they react with substrates. So to begin, we're going to look at two simple equations. The first being how enzyme plus substrate equals the enzyme-substrate complex. And then from there, the enzyme-substrate complex becomes enzyme plus product. And as you can see, the reaction arrows here have all separate constants for each reaction. So the forward reaction here, where enzyme plus substrate forms the enzyme-substrate complex, is K1, and the reverse reaction of that would be denoted by K-1, and then K2 would denote the product formation equation. As you can see, if you factor out all of the enzyme out of this equation, you would get substrate yielding to product. So that way we know we're on the right track with this equation. So to take this information, we will need to look at the steady state assumption. So the steady state assumption is that ES is equal to the sum of all the reactions decreasing its concentration. And it can be denoted by this equation here, where you have the instantaneous rate of change of ES divided by time equals K1 times the enzyme concentration times the substrate concentration minus K-1 times the ES complex concentration minus K2 times the ES complex concentration, which is all equal to 0. And as you can note from this equation here, we're looking at the reactants from the previous equation. So for K1, the reactants would be E and S, and ES for the K-1 and K2 reactions. And so from there, we can take this equation, and we're going to want to isolate this little factor here, this enzyme concentration. And we can do that by taking the total number of enzyme, which can be denoted by ET, and we know that ET is equal to the enzyme concentration plus the ES complex concentration. So from there, we can do simple subtraction to get the enzyme concentration, which is equal to ET minus ES. And now that we know this value, we can plug this into our previous equation for E. And that looks a little bit something like this. So you have the instantaneous rate of change of ES divided by time equals K1 times the total enzyme concentration minus enzyme substrate complex concentration times the substrate concentration minus K-1 times the ES complex concentration times K2 times the ES complex concentration. And we're still all equal to 0 here. And so for the next part, we're going to want to FOIL out this K into this expression here. So we're going to put FOIL in K and we're going to FOIL in S. And that equation will look a little bit something like this. And we kind of already took out the instant rate of change expression out because it's equal to 0 also. So we're just putting 0 equals K1 times the total enzyme concentration times the substrate concentration minus K1 times the enzyme substrate concentration times the ES concentration, or the substrate concentration, minus K-1 times the ES complex concentration minus K2 times the ES complex concentration. And so from here, we're going to want to isolate ES. And to do that, we're going to put ES on one side first. So we can do that by moving it over where this 0 is, and it'll look a little bit like this equation. And so to further isolate it, we're going to want to divide this by this. And you can see that being done here. And you end up with the following equation here, where you've got ES complex concentration equals K1 times the enzyme total concentration times the substrate concentration divided by K1 times the substrate concentration plus K-1 plus K2. So from there, we can clean up this expression a little bit by using the reciprocal. So we're going to multiply both the numerator and the denominator here by 1 over K1, which leaves us with the resulting equation, the ES complex concentration times the total enzyme concentration times substrate divided by substrate concentration plus K-1 plus K2 over K1. And this red expression here is the Km. And the Km is the Michaelis-Menten constant. And this constant is unique to each enzyme, and it's independent of enzyme concentration. And we'll talk a little bit more about Km once we get to Vmax and kind of what its significance is. So we can take this expression here, and we're going to look at instantaneous rate of change for products. So from up until now, we've been working on the first two equations, or the first forward and backwards reactions in this step. So now we're going to look at the K2 reaction a little bit. So the instantaneous rate of change for a product, or our initial velocity, is a function of the reactants from the equation where ES yields E plus P. So the ES concentration is the only reactant for this reaction, and we now know from the previous slide what that equation looks like. So we can substitute that in when we're multiplying by K2, and when you plug that K2 times ES, you end up getting the Michaelis-Menten equation. So here's what the early version of that equation looks like, where you have initial velocity equals Kcat times the enzyme, the total enzyme concentration times the substrate concentration divided by the substrate concentration plus Km. So that equation looks a little strange because we don't know what Kcat is. So what is Kcat? Kcat is roughly equal to K2. This value is also known as the turnover number, or the maximum number of substrates that can be converted to a product per active site per time. So why is that significant? Because when you multiply the turnover number, which is the maximum number of substrates, times the E total, which is the total number of enzyme, you get Vmax, which is the maximum velocity attained when total enzyme is bound to substrate. And this will be included into our equation, and we can substitute Vmax into Kcat times E2 into our equation to get the final equation. So next, back to Km and how it relates to Vmax. Km is half of Vmax when it is equal to the substrate, and we can see that through this visual equation here, where if we have 2s, because s is equal to Km, we end up with Vmax divided by 2. So Km, when it is equal to the substrate, is Vmax divided in half. And so we can take this equation and what we know here, that this is equal to Vmax, and create the following final Michaelis-Menten equation.